Do you know that you have experienced making solutions before? Sometimes your solution is going to be dilute, and sometimes your solution is going to be too concentrated, but always tasty. Today's lesson is on calculating the strength of concentrations. So often in consumer products, where liquids dissolved in a liquid, such as drinks and cleaners, we calculate the percent by volume. So the symbol percent, comma, V by V is used to delineate that. So to calculate percent by volume, we take the volume of the solute, divide it by the solution, and multiply it by 100 to get 100%. So to solve for the volume of a solute, we can rearrange our equation to be C divided by, or C percent, divided by 100 times the volume of the solution. And that will give us the volume of the solute. I'm going to run out of room there. So the volume of the solute. Now, to solve for the volume of a solution, we're going to put our volume of the solution here. And this is going to be equal to the volume of the solute divided by concentration times 100. And again, sorry, the concentration is C as a percent. So that is how we find the volume of the solution. So, for example, a 300 milliliter bottle of hydrogen peroxide solution contains 18 milliliters of peroxide. What percent concentration is the product? Now, because both these volumes are in milliliters, we don't need to convert them to the standard unit of liters. So we'll take our solution, volume solute divided by volume solution times 100, put in our values, and we get a 6% concentration by volume solution. Now, example 2, a fruit beverage advertises itself as 45% fruit juice. So what volume of fruit juice is found in a 2-liter jug? So we're going to take the concentration, multiply it by the solution, and we'll have the solute. So we've already divided it by 100, which is going to turn 45% into 0.045. So multiply that by 2 liters, and the volume of the solute is 9 liters, and that's going to be the water that's in that fruit juice. Or we can say we have 0.45 times 2,000 milliliters, and 9,000 milliliters is the volume of our solute. So just different units in that answer. So parts per million is useful for concentrations where there's a very, very small amount of solute in a large amount of solution. So typically we'll use parts per million when we look at pollutants in water. And the symbol used is ppm. So 1 ppm is equal to about 1 milligram of solution per 1 liter, or 1 kilogram of solution. And in water, 1 milliliter equals 1 gram. So to calculate parts per million, we take concentration in parts per million is equal to the mass of the solute divided by the mass of the solution times 10 to the power of 6. So rearranging the formulas for concentration by parts per million give us the following formulas. So to solve for the mass of the solute, we're going to end up with mass of the solute is equal to the concentration in parts per million times the mass of the solution divided by 10 to the power of 6. To determine the mass of the solution, we end up using the formula mass of the solute times 10 to the power of 6 divided by the concentration in parts per million. And these original formulas are given to you in your data booklet, and working through algebra, you're able to rearrange them to solve any problem that you need. So for example 3, the allowable level of fluoride in our drinking water is 1.5 milligrams for every liter of water. So how many parts per million is the allowable level? So again, 1 liter of water equals 1,000 grams or 1 million milligrams. So that's why we end up multiplying it by 10 to the power of 6 for that million. So we take the mass of the solute divided by the mass of the solution, 0.1 milligrams divided by 1 million milligrams times 10 to the power of 6, and we end up with 1.5 parts per million. So this is the maximum allowable fluoride in our drinking water. In the middle of spring, pollen levels can reach 5,000 parts per million. So we want to know what mass of pollen would we inhale if we breathed in about 9.6 grams of air. So we're going to be looking for the mass of the solute. So our formula is now going to be mass of the solute equals mass of the solution times parts per million divided by 10 to the power of 6. So 5,000 parts per million divided by 10 to the power of 6 times 9.6 grams gives us a total weight of our solute, mass of our solute of 0.048 grams, or 48 milligrams of solute. The amount of moles in a solute per solution that is used in labs is typically measured in molar concentration. So for this one, the volume must be in liters. So if we're given anything in milliliters, we must convert it. The symbol mole is often referred to as molar concentration. So a standard solution is going to be a solution that we have a known concentration, and we want to calculate this for our different formulas. So concentration can equal moles per volume, and moles also equals mass over molar mass, and these moles are the exact same. So we're able to rearrange these two formulas to solve for both moles and per volume. To solve for moles, we have moles is equal to concentration multiplied by volume, and volume is equal to moles divided by concentration. Now to solve for mass, we have mass is equal to the amount of moles times the molar mass, and to solve for molar mass, this equals mass divided by moles. So if we're doing a two-step question where first we have to calculate the moles because we were given the weight of a substance to make a solution, we don't want to round off from the calculator before we move into our second step. We want to keep that unrounded number stored in our calculator, and if that's not possible, to keep as many decimal places as possible. So for our first example, what is the concentration of an acid that has 0.50 moles of solid hydrogen sulfate dissolved in 2 liters of water? So we were given the moles at 0.50 and the liters in 2 liters. So our units are correct. So our concentration is 0.25 moles per liter. In example 6, we're given the mass of this solution that will be dissolved in milliliters of water. So we currently don't know the moles yet, but we can convert our liters from 300 milliliters to 0.3 liters of water. So using our other known equation, we're going to calculate the moles of sodium sulfite by calculating the molar mass by using the molar mass of water and the mass given in the question. So the molar mass of sulfate we find by multiplying 2 by the weight of sodium, a mole of sodium at 22.99 grams per mole. Add that to the molar mass of 1 sulfur at 32.06 grams per mole, and 4 moles of oxygen at 16.00 grams per mole. So giving us a total molar mass of 142.04 grams per mole. So the moles in 30 grams of sodium sulfate is 0.211 moles. Now we want to keep this to our 3 decimal places as we move it over to our concentration formula. So the concentration of a solution where 30 grams of sodium sulfate is dissolved in 0.300 liters of water is 0.704 moles per liter. So again, we need to make sure we're using the right units and making sure we have the correct information, in this case moles, to solve the concentration. So if 50 milliliters of a 2-mole solution of copper 2 sulfate contains what mass of solid copper 2 sulfate? So we're going to go backwards from our concentration to our from our volume and solute volume and moles to find the mass that was originally put in that solution. So we can calculate the mass of copper 2 sulfate or copper sulfate by taking the mass of copper, multiplying it by the molar mass, or adding it to the molar mass of copper, sulfur, and 4 moles of oxygen at a total molar mass of copper 2 sulfate of 159.62 grams per mole. So our moles or our concentration is 0.200 moles per liter, and we have 0.05 liters of that solution. So our total moles in the solution is 0.010 moles. Now transferring over that to our moles is mass over molar mass, rearranged to be mass is moles times molar mass. We take our 0.010 moles from our solution and add it to multiply it by 159.62 grams per mole, which we can figure out with our periodic table, and we get a total mass of 1.60 grams. So multi-step processes, you want to keep all the decimal places possible. Make sure you're referring back to your periodic table to find the molar mass of different substances, as well as to refer back to the different formulas you can use. So identify what variables you have and what would be the best formula for that problem. So when we look at dilutions of solutions, we typically will add more solvent to a solution to make it more dilute. This means that the quantity of solute does not change, but the number of moles of solute will stay the same. So the formula to calculate molar concentration when performing a dilution is CIVI, or initial concentration, initial volume, is equal to CFVF, or initial concentration multiplied by initial volume. Because the moles are going to be the same, we do not have to put them on the product or the first or second side. Now you can use I's and F's for initial and final, or you can use 1's and 2's for before and after. They're just our subscript identifying which side of the reaction will be on. So because the two volumes will cancel out, as long as the units are the same, there's no need to convert them. So we either want to have them both in milliliters or both in liters. And because we're making a list of 4 different variables, because we're dealing with 4 different variables, you should make a list of what you were given in the question and what is your unknown. So a 50 milliliter of a standard 1.00 mole per liter solution of hydrochloric acid is diluted to 200 milliliters. What is the new concentration? So both our volumes were in milliliters, 50.0 and 200 milliliters, so we don't need to do any unit conversion. Concentration is 1.00 moles per liter for the initial solution. We're looking for our final solution, final concentration. So starting with our initial equation, CIVI equals CFVF, we can change that into CF equals CIVI divided by VF, or the final volume. So our 1 mole per liter solution multiplied by 50 milliliters divided all together by 200 milliliters. And again, it's okay to leave them in milliliters because they're going to cancel each other out. Gives us a final concentration of 0.250 moles per liter. For our last example, we're going to take 50 milliliters of the same standard solution and dilute it to 0.50 moles per liter. What's the volume of the final solution? So we still have our 2 initial concentrations and volumes. Our final volume concentration is going to be 0.5 moles. Now we want to see what the final volume is. So rearranging our formula to be VF equals CIVI over CF. And again, the units of moles per liter will cancel out, giving us our answer in milliliters of 1.00 times 10 to the 4 milliliters, or 1 liter. So those are all the different calculations we can do to look for concentration, percent, parts per million, or molar concentration, as well as our dilution concentration formulas. I hope you enjoyed today's lesson. Bye.
If you enjoyed this video, check out our website, online.plrd.ab.ca, and visit us on Facebook, Prairieland Online Academy. You can find out all that's going on with Prairieland Online Academy.